among other things, Albert Einstein was particularly famous for the equation that was named after him, Einstein's equation. And Einstein's equation goes something like this. So what this tells us is that the energy is equal to the mass of an object times c squared, which is the speed of light. So remember, this is mass, not to be confused with weight. So how much stuff something contains. This is just the speed of light. And this is energy in joules. So the equation itself is relatively simple. We're just talking about energy, mass, and a fixed constant, the speed of light. But what this tells us is, previously we've talked about that you can't create or destroy mass or matter. But Albert Einstein discovered these experiments, and particularly when we talk about radiation, that mass is actually being reduced. When we look about the decay, the sum of the components doesn't equal the original component. And so the only way that he could explain this is that there is some relationship between mass and energy, and they're actually interchangeable. So if you do stage 2 year 12 physics, we talk about this in a bit more detail about how mass and energy are actually very strongly related. And some things can be massless, but because they have energy, they can still exert a force on an object. Whereas typically forces and gravity can only apply to things with mass, we can now interchange and say, well, energy can act like mass does. This is really powerful, and the reason that we can sort of use this, apart from calculating the energy that's released in a nuclear reaction and things like this, is you can strongly relate it to the matrix. A good example of this is, let's say that we are in the future, probably not that far down the track, and we've got this energy crisis. What do? Where do we get these abundant amounts of energy from without consuming fossil fuels? Well, what about people? Maybe the matrix had something going on. What if we use people as batteries? How much energy can a person actually produce? Well, let's think about it. If we use our E equals mc squared equation, let's say we'll use me as an example. How much energy do I actually have to give as an energy source? Well, it's just equal to my mass, which is conveniently enough a nice round 100 kilograms, and it's times the speed of light squared. So the speed of light is 3 times 10 to the 8 meters per second, and we square that. And then if I just crunch those numbers in a calculator, I get 8.98 times 10 to the 18 joules. So if you think about it, that is 8.98, or 8 with 18 zeros after it in terms of joules. So even if I want to convert that to kilojoules, I only drop by 3. So that'd be 8.98 times 10 to the 15 kilojoules. Which I don't know if you've looked at your daily intake, but it's certainly nowhere near this. So this is just how much energy my body, purely because of my mass, could give. So if we could find a way, and I'm not saying this is ethically plausible, but if we could find a way to actually use our body as an energy source and consume it like batteries, like in the Matrix, this is a monster amount of energy. You could produce enough energy off a single person to power a city comfortably for quite a long time. But that's not really what Einstein was talking about. His equation was specifically talking about other types of physics, and we'll use this a lot within the nuclear topic to calculate how much energy is released based on the change in mass. So if we look at an object with a certain amount of mass, let's just say, for the sake of a number, that we have 20 kilograms of a substance. It decays and breaks down and does all this stuff, and then by the end of it we drop and we've now got 15 kilograms. So in the kind of questions that you'll see, we figure out what the difference in mass is, which in this case is quite easily 5 kilograms. And then I use that 5 kilograms to say, well, if I lost 5 kilograms in mass, I can't create or destroy it, it must have been emitted in energy. So I plug in my E equals mc squared equation, punch the number, and I get the amount of energy that was released within this reaction. So that's, for this course, this is the powerful application of it. Particularly, you need to know that I figure out the change in mass. So if I was given the actual atomic structure, let's say I started with H3, my deuterium, or tritium, sorry, and it decays down, it doesn't necessarily do this, but it decays down into this. Then I figure out what is the change in mass. I've lost how many neutrons? I've lost 2 neutrons. I figure out what is the mass of those 2 neutrons. and then that becomes my change in mass. I plug that into E equals mc squared, and that's how much energy I've released. So this is not necessarily what happens, it's just an example of how it would be represented. So that is using Einstein's equation.
Tell me pretty lies, look me in the face, tell me that you love me, even if it's fake.